An exponential function is of the form y equal a to the x. And basically we have two types of exponential functions. One where a is greater than 1, and the other one where a is less than 1, but it's always going to be positive, greater than 0. All right, so for example, a greater than 1 we can have in that category something like y equal 2 to the x. And for a less than 1 we can have something like y equal, let's say, 1/2 to the x, which is the same thing as 2 to the minus x. All right, and what do these look like? Well, something of this form, where a is greater than 1, is going to increase as x goes to infinity. All right, so basically the graph, just all these graphs where a is greater than 1, well, they all are going to go through 1 on the y-axis, because if we substitute in 0, we get 2 to the 0, which is 1. Anything to the 0 is 1, so they always go through 1. All right, now if a is greater than 1, they're going to increase on the right. And when x is negative, we have things like 2 to the minus 2, 2 to the minus 3, 2 to the minus 4, which is 1 over 2 to the 4th. All right, and so they're going to go down here. Okay, they always stay above y equals 0 and get closer and closer. We have an asymptote right here, horizontal asymptote. The x-axis. All right, and here we have sort of the opposite picture. This flipped around the y-axis. Remember that when x is replaced with minus x, that's a reflection through the y-axis. So that's basically what we have here, x replaced with minus x. So here, reflect through the axis. Again, we're going to go through 1 still on the y-axis. And here, just think of replacing x with things like 1, 2, 3, 4. 1 over 2 to the minus 4 is 1 over 2 to the 4. So that's 1 over 16. So that's going to go down here. And if x is negative, then minus x is positive, and we're going to start getting larger and larger numbers. All right, so we're looking at y equals 3 to the minus x. Let's just graph this a little more precisely. All right, y equals 3 to the minus x. Remember, we can think of this as 1 over 3 to the x, or 1/3 to the x. So when x gets larger, like when x is equal to 2, we're squaring 1/3, so we have 1/9. All right, let's just do a little table of values to help with the graph. Okay, when x is equal to 0, y is 1. When x is equal to 1, we have 1/3. 2, we have 1/9. 3, we have 1 over 27. So you see that as x gets larger, y is getting smaller and smaller, closer to 0. Now, when we substitute in negative values, like -1, we have 1/3 to the minus 1, so that flips the 1/3, and we get 3 to the 1. If we substitute in -2, we have 1/3 to the minus 2. Again, it flips, and we get 3 squared, or 9. And -3, again, that flips this, and we get 3 cubed, or 27. So we see as x gets negative and goes to the left, these values get bigger. Let's just try to do a rough sketch now. All right, let's say this is 1 on the y-axis, 0, 1. And when x is equal to 1, y is 1/3, something like this. This is 1 comma 1/3. And we'll just do 1/9, which is very, very close to the x-axis. So This is 2 comma 1/9. All right, now let's put in -1 here, and we have 3 for the y value. And I'm not going to do -2 because I would go off the page here. So we can imagine that this is going up pretty steeply on the left, and then it goes down. Getting closer and closer to the x-axis, never touches the x-axis. All right, so here we have a horizontal asymptote. Let's talk about the domain. Well, we can substitute in any x value, and we on the right and on the left. So the domain would be all real numbers, or we could say x between -infinity and infinity. And what about the range? Well, we always have positive values here. All these values, or the graph, is above the x-axis. So positive y values. So the range is y greater than 0. Okay, here we're going to evaluate y equal 27 to the x equal 2/3. So let's do that. So we're doing 27 to the 2/3. First we'll do the denominator. That means take the cube root of 27, which is 3. And now let's square that. Now we have this numerator here, and so we get 9. In number 3, we're evaluating 1/3 to the x plus 1 equal to 81. So let me just write that down. 1/3 to the x plus 1 is equal to 81. What we want to do is, if we can change both to base 3, then we can set the exponents equal to one another. So on the left, that's just 1/3 to the x plus 1 is 3 to the minus x plus 1. Okay, so here we have base 3, and 81 is 3 to the 4th. So now we have base 3. So just take these two exponents and pull them off and write down this little equation. And just solve for x. -x minus 1 is equal to 4. Negative x is equal to 5. So x is equal to -5. In number 4, we want to graph and find the domain and range of y equal e to the x. So this is an exponential function. The base e is approximately 2.71, so it's greater than 0. All right, we already saw the graph of y equal 2 to the x. The graph of y equal e to the x is going to be similar. All right, we'll do a little table of values. When x is equal to 0, we have e to the 0, which is 1. If x is equal to 1, we have e to the 1, which is e. And if x is equal to -1, we have e to the -1, which is approximately 1 over 2.71. I'll just write 1 over e. All right, not too many values, but we know the approximate shape of this curve. Because it is an exponential where the base is greater than 1, so we know it's going to go up here, go through 1, and down, and have a horizontal asymptote here. So let's make this 1. Let's plot the other values. E to the 1 is e. Here's 1. Here's 2. Let's say this is 3. So 2.71, let's put it over here. Okay, and here we have e to the -1, which is 1 over e, 1 over 2.71, which is a little bit bigger than 1/3 over here. And we'll just connect. Remember, we know that we have a horizontal asymptote as x goes towards -infinity. Okay, so that's our graph. Let me just put in these values. This is 1 comma e. This is 0 comma 1. And this is minus 1 comma 1 over e. And now for the domain and range, well, we can see that by looking at the graph. We can substitute in any x value, or this graph goes all the way to minus infinity, and this graph goes all the way to the right slowly to positive infinity. So the domain is x greater than minus infinity and less than infinity. And the range, well, this graph goes all the way up to infinity, but it doesn't go all the way down. It levels off above y equals 0. So the range is y greater than 0. In number 5, we'll use the formula for finding the amount of an investment that's compounded a few times a year. So here's our formula. The amount is equal to P, that's the initial investment, the principal, 1 plus the yearly rate divided by the number of times the interest is compounded, times, raised to the exponent nt. T is number of years, and n, number of times the interest is compounded. All right, so that's our formula, and we're going to apply that here. So we have A is equal to the initial investment of 1,000, 1 plus the rate. Now the rate written as a decimal, so 0.04, divided by the number of times it's compounded, that's twice a year, so 2, and the number of years times the number of times compounding, so that would be 2 times 15. All right, so we're just looking at 1,000. This is 0.02, so we're 1 plus 0.02, that's 1.02 to the 30. All right, so we'll use our calculator to evaluate this. Okay, so 1.02 to the 30 is approximately 1.811 multiplied by 1,000, and we have $1,811 after 15 years. In number 6, the numbers are the same as in number 5. We have an investment of $1,000, 4%, but this time compounded continuously for 15 years. So we have a different formula. So here's our formula. The amount is equal to P, e to the RT, where R is the rate in decimal format. So 1,000 for the initial amount, E, and R would be 0.04. T, in this case, T is 15. So we'll substitute in 15 years. So we're looking at 1,000 multiplying 1,000 e to the 0.6 for 0.04 times 15. And we'll look on our calculator for this value. So that's 1,000 times 1.822 approximately. Okay, so let's multiply that out, and we have $1,822, so just a little bit more than what we would get if we compounded twice a year, just a bit more.